Okay, so let's start with this reading this question. 4 students tested their reaction times using a computer program. When a green light appeared on the screen, the students had to press a key. Table 3 shows the results. So we have the 4 students, 2 boys and 2 girls. They did 3 tests, and then they've taken the average of the reaction times here. What is meant by reaction time in this experiment? So we go back to the question. When a green light appeared on the screen, the student had to press a key. So
it's the time taken the student to press a button after seeing a green light. Right? How quickly did they react to that? So next bit says boy 2 has an anomalous result in test 2. Suggest the reason why.
Just out of interest, boy 2, this result looks like it doesn't fit the pattern, so it would be called an anomaly. But why might there be an anomalous result? So
the boy could have been distracted.
A few other things could have happened. I mean, the person measuring the reaction time, I suppose it's a computer. There could have been an issue with the mouse, but just keep it simple. Try and aim for the most straightforward answer that's likely to be on the mark scheme. Give one conclusion that can be made from the results in table 3. Right. So there's quite a few things you can look at. You can look at how going from test 1 to test 2 to test 3, on average you can see the reaction time is going down. So 0.28, 0.27, 0.26. The same with this one, ignoring the anomalous result. In fact, all of them, right? As we go on and they practice more, the reaction time is going down, right? So that's something we could say. Practice brings the reaction time down. And another thing we could say is if you compare the boys' results to the girls' results, the boys' results on average are lower than the girls' results. So you could choose either. Let's go with...
boys have a faster reaction time.
Right in there. Okay, next bit says, suggest further evidence that you could collect to support your conclusion. Well, we've only compared 2 boys to 2 girls here, so I think you would need a larger sample size. So
you could repeat with a larger sample size, e.g. 100 boys versus 100 girls. Okay, so
that would certainly make it a more reliable test. Right. Reaction time is important at the start of a race. Table 4 shows the time taken by a boy to run different distances. So 100 meters, 12.74, pretty fast for a student, I would imagine. Not for Usain Bolt, but fast. As we're about to watch here, Usain Bolt doesn't get everything right first time. No one does. One of my big mottos is be proud of your mistakes, so you can learn from them. Don't hide them. But yeah, look, this is a false start at a World Championship race.
Oh my word, it's a false start. I think Usain Bolt's false started. No. I can't believe it. I think Usain Bolt, almost unthinkably, I was talking about the fact that...
Let's have it one more time.
Oh my word, it's a false start. I think Usain Bolt's false started. No. I can't believe it. I think Usain Bolt...
So obviously so keen to get going, he's gone early. 200 meters 25 and 800 meters 100 and nearly 40. Reaction time is more important in a 100-meter race than in an 800-meter race. Okay, so let's just imagine you've got quite a slow reaction time. Let's say it takes you a whole second to respond to the gun. Boom, and then you go. If you could run 100 meters in say 10 seconds, like say Usain Bolt does most of the time, then your 10 seconds, that 1 second reaction time is 10% of the race. So if you could make your reaction time only half a second, you will save yourself 5% of your total race time. So it will make a big difference. 10% saving, quid's in, right? But let's just say that you're looking at that 1 second out of your 800-meter race. Well, here he's roughly about 140 seconds, so it's 1 out of 140. And 1 out of 140 is 0.07%, right? So a much smaller percentage. So what we need to say is that
we're in the 100 metre race. In the 100 metre race, reaction time is a larger percentage of the time taken to complete the race. Right, so it's a larger percentage of the time taken to complete the race. In the 800 metre race, it is a much smaller percentage. Okay.
Right. So now we have what looks like it's a graph. First thing to do when you see a graph is it's like reading a book. You wouldn't go to page 4 of the book and start reading there. You have to read page 1. Page 1 is read the y-axis, read the x-axis, check the units of each. Okay. If you do this, it's like reading the first 2 pages of the book. Or if you don't read them, you won't know what the hell's going on. So it's a distance time graph. Okay. It's a distance time graph, and we can start looking at what's going on for 2 girls. So it's girl A did the race like this, and girl B did the race like this. Girl B finished sooner, so she must have won the race, and girl A took 160 seconds to complete it. Right, now let's have a look at the question. Compare the motion of runners A and B. Right, and it's look at this, a 6-mark question worth a lot of marks. Right, so I'm going to take a note from Miss O'Grady, and she suggested that you should go to the graph and you should make a few comments on the graph, annotate the graph, right? So let's have a little look. Now I know that on a distance time graph, that the steeper the line, the faster the object. This is really fast and this is slower, okay? And how do I know that, or what makes that, how do I keep that fresh in my mind and easy to remember? Well, I always think about it as the distance time graph as being like a photograph of my house here and say the chip shop here, right? And if I can go from my house here, right, to the chip shop in a very short amount of time, so this is a small amount of time, I'm going fast. But if it takes me a very long amount of time to get to the same chip shop, I'm going slow, right? So steep lines are fast, shallow lines are slow. And if the line is getting steeper, its gradient is getting steeper. So down here the gradient is low, down up here the gradient is high. So it's getting faster. This is acceleration. Acceleration, however you spell that. Right? If the line for a distance time graph is getting less steep, then it is deceleration, de-acceleration, or however you want to pronounce it. Right, so now that we've kind of summarised all that kind of stuff and reminded ourselves, let's have a little look. So A looks like the gradient is pretty constant. They do a constant speed, so constant speed, because the steepness stays the same. Then they seem to start to slow down at around 80 seconds, so slowing down, or decelerating, slowing. And then they finish at what time? At 160 seconds, right? So that's all useful information. What can we say about B? So for B, the gradient starts here and it gets steeper and steeper. So B is accelerating the whole time. B overtakes, because if you think about it, B has now got in front of, B is at 800 meters at, let's work this out. So there is 20 divisions between here and here. Sorry, there's 20 seconds between here and here, right? That's 20 seconds. And there are 10 squares, so that means each square is worth 2 seconds. So this is 126 seconds. So B, if we follow that line down, try and draw a straight line, it's quite tough. B finishes at 126 seconds. It gets to the 800 meter mark at 128 seconds, whereas A takes a full 160 seconds. That's another important point. And a really cool spot as well to look at is that B overtakes A at a time of, let's try and get this exactly right, at a time of 110, 102, 104 seconds. So we have an overtaking event at 104 seconds. Right, so I think I've got a load of good stuff to write about now for my 6-mark question. So it's just a case of trying to get that down on the 6-mark question. So I'm going to actually just write underneath here so we can still look at the graph. Right, so let's try and make 6 sensible points.
A starts faster because it's got a steeper, the line is steeper here than it is here. So A starts faster than B. That's 1 mark, hopefully. Right, A starts at a constant speed and then slows after 80 seconds. Yeah, this is where we said it was slowing down, right here, at 80 seconds, and then slows at 80 seconds. Right, so that might be worth 2 marks, I'm not sure. 3, what else can I say? Let's mention B then. B starts slow and accelerates for the first. So look for the first. Well, actually, it looks like they accelerate for the whole thing. So B starts slow and accelerates, overtaking A at, what time did they overtake at? 104 seconds, at 104 seconds. Right, that's 3 good points. In fact, these are double barrel points maybe, so I'd probably get a few more marks than that. And then let's talk about when they both finish. So A finished at, what time? A finished at 160 seconds. And B finished at, here it is, 126 seconds. Right, and just one final point. B was definitely the winner. Right, so...
Although I've written 5 points here, I think I will definitely get all 6 marks because some of these points are doubling up, like this is 2 points in one and this one is 2 points in one. So hopefully I've said enough to get all 6 marks. The key thing here is a lot of students will see 6 marks or not even check the number of marks available and just panic. Go back, if you have a diagram, it's a really good idea to sort of sketch it out on the diagram and try and plan it out like that. Check your work, exactly. Right, so that is question 6. Thanks for watching.